Hey everyone, in this video we are going to talk about K-maps. Now this topic will be covered over the course of two videos. So in part 1 we are going to start with an introduction to K-maps, then we'll take a look at 2, 3 and 4 variable K-maps, and then we'll discuss some techniques for K-map simplification, specifically product of sum and sum of products. So let's first start with an introduction to K-maps. Now, Boolean expressions sometimes need simplification, otherwise the resulting logic circuits become too complicated. For instance, consider this expression, right? If we were to form a logic circuit to realize this expression, it would look something like this, right? This is a logic circuit for this Boolean expression, and you can kind of see how complicated this circuit looks. Now, if we could simplify the given Boolean expression, we would be able to simplify the resulting logic circuit naturally, right? So if we could somehow simplify this expression into this expression, the resultant logic circuit would be like this. So basically what we've done is we have converted this circuit into this circuit with the help of simplification. They both produce the same output because this is essentially a simplified version of this one, right? And this circuit is so much more simpler than this one. And this is the advantage we get when we simplify Boolean expressions. Now, Boolean expressions can be simplified using Boolean postulates and theorems, but that is a time-consuming process. Plus, the simplified expressions need to be rewritten after each step, so it's complicated, it's time-consuming, and it requires a lot of resources. Now, to overcome this difficulty, Carnot introduced a method for simplification of Boolean functions in a very easy way. So this method is known as Carnot map method, or simply the K-map method. So that's where this term comes from. K is essentially short for Carnot. So let's take a look at what these K-maps look like for 2, 3 and 4 variable functions. So first let's start with the 2 variable function. 2 variable function, which means we have A and B. Let's name these variables A and B. And this is what a K-map for a 2 variable function looks like, right? Now, these are Boolean functions, so Boolean variables. So both of them can have either a value of 0 or a value of 1, right? So here we have 0 and 1, which are the two possible values for the variable A. And similarly, here we have 0 and 1, which are again two possible values for the variable B. Now, since we have A can be either 0 and 1, B can be either 0 and 1, so the resultant map looks something like this. It has 4 cells. And here in the gray, we have essentially given numbers to these cells. So what these numbers represent are essentially, these numbers are the decimal equivalent of the code words which address the K-map cells. So in this case, we have 4 cells. We start the numbering with 0, right? And then 0, 1, 2, and 3. And this essentially, this completes an empty K-map for a 2 variable function, right? What we do with these maps, we're going to discuss in the upcoming slides. But for now, all you have to understand is what a K-map for a 2 variable function looks like. Now let's move on to a 3 variable function. So what this means is now we will have 3 variables in our equation, A, B, and C. Like in this example, right? In this example, we had 3 variables, A, B, and C. So this is what a K-map for a 3 variable function looks like, A, B, and C. Again, A can have 2 values, either 0 or 1, and the combination of B and C, since we are putting both B and C over here, their combination can take 4 values, right? Both B and C can be 0, 0, or B can be 0 and C can be 1, or B could be 1 and C could be 1, or B could be 1 and C could be 0. So these are the 4 possible combinations for these 2 variables taken together. Now what's interesting, what's important in fact here is that this right here is a gray code labeling of rows and columns. You'll see that this goes 0, 0, 0, 1, 1, 1 and 1, 0. Not 0, 0, 0, 1, 1, 0 and 1, 1, which is how your binary variables progress, right? So this is important. This labeling right here has to be gray code. And gray code we have discussed in this course already, right? And then we have, in this case, we have a total of 8 cells in this table. And these are again the decimal equivalents of the addresses of each of these cells. We start with 0 and we put these numbers like this: 0, 1, 2, 3, 4, 5, 6, 7. So this is the ordering, and this ordering is important. Alright, so this was a K-map, again empty K-map for a 3 variable function. Now what happens in case of 4 variables? What if our equation had 4 variables, A, B, C and D? So the resultant K-map looks something like this. So we have A and B on one side of this map, C and D on the other side of this map. Again, the labeling goes 0, 0, 0, 1, 1, 1, 1, 0, just like we did in case of 3 variable K-map. Alright, 0, 0, 0, 1, 1, 1, 1, 0. And the numbering of the cells goes something like this: 0, 1, 2, 3, 4, 5, 6, 7, and skip a row, 8, 9, 10, 11, come back to the skipped row, 12, 13, 14 and 15. Alright, so the numbering and the labeling, these are the two important things you have to keep in mind while drawing a K-map. So now we have seen K-maps for 2, 3 and 4 variable functions. Now we'll proceed to the next challenge of K-map simplification, which is the actual simplification. How do we simplify Boolean expressions using K-maps? So before we start with the simplification process, there's a term called minterm, whose meaning we have to understand. Now a minterm is a Boolean expression resulting in 1 for the output of a single cell and zeros for all other cells in a K-map or a truth table. So what this means is, suppose we have a truth table that looks something like this. Alright, we have 3 variables. So if we had to draw a K-map, it would be a 3 variable K-map, A, B and C. So these are the variables. These are the variables in the Boolean expression. The truth table is given now. Alright, and this is the output. So a minterm represents those terms whose output is 1. Alright, so let's see in this table, this is a 1, this is a 1, this is a 1, this is a 1 and this is a 1. Alright, so these are the minterms. This is what we mean by minterms. In this truth table, we see 5 minterms. What are those? This one, which is A dash, B dash, C. The second minterm is this one, which is A, B dash, C dash. Look here, right? This is the third minterm, which is A, B dash, C. This is the fourth minterm, A, B, C dash. And the fifth minterm is A, B and C, right? So basically minterm is any entry of this table for which the output is 1, right? Because only for these combinations we get a value of 1. For all others we get zeros. So these are the minterms. Very simple, right? So let's move on now. Now if we have to represent a truth table in the form of minterms, again it's very simple. This was the truth table that was given to us. We can write it like this because this is a function of ABC. This is a function of ABC and this function can be written like this. And what are these? These are essentially those entries of this table which have an output of 1, which is 1, 4, 5, 6, 7. If we start with the numbering, this will be 1. This will be 0, this will be 1, this will be 2, this is the third one, this is the fourth one, this is 5. We're just simply counting the rows. You can think of this as simply counting the rows. Now, in which of these rows does a 1 appear? In first, fourth, fifth, sixth and seventh. So first, fourth, fifth, sixth and seventh. So what we are doing essentially, we are simply listing the minterms. These are the minterms, right? We recognize these minterms. So in the form of minterms, this truth table can be represented like this. We simply list the minterms because we know that all the rows whose number is not mentioned here must have an output of 0. So no need to represent both zeros and ones. Simply just write all the rows that have an output of 1, and all the rows that are not mentioned here will naturally, that would mean that they have an output of 0, right? So no need to mention them. This right here is a summation function. And this is actually important. So we'll come back to this later. All right. All you have to remember for now is when we're talking about minterms, we have to use a summation. All right. Now you know how to represent a truth table in the form of minterms alone. Okay. Now here we see how to convert this expression, which was basically just a list of minterms, into a K-map, which is essentially what we had to do in order to start simplifying the K-map, right? So first what we need to do is either the Boolean expression or the truth table needs to be converted into a K-map, and this is how we do it. So we already know that this is what a K-map for a 3-variable function looks like, right? A, B, and C. And these are the numberings which you have already seen how to give these numbers. Now all we have to do is put a 1 in all those cells whose number is mentioned here, right? All those cells whose number is mentioned here will get a 1 and all the remaining cells will get a 0. Very simple. So 1, I put a 1 here. Next was 4. So I put a 1 here. Next was 5. So I put a 1 here. 6, another 1, and 7, another 1 here. These were left, so these are my zeros. And now this is your final K-map for this truth table. Right? So you could either be given a truth table or you could be given an expression like this, just in the terms of minterms, and all you have to do is put a 1 in those cells whose number is mentioned here and put a 0 in all the remaining cells, and this gives you the K-map. Now the next step is to actually simplify this. So we're going to simplify this K-map, which will, what it will do is, it will in turn simplify this expression, which will in turn simplify this truth table, which is what we are intending to do. So let's see how to simplify this K-map. So suppose we are required to simplify this expression. Again, see, this expression is given purely in terms of the minterms. No truth table is given. But if you had been given a truth table, you know how to convert a truth table into something like this. And then you can write this in the form of a K-map. Now simply here in this case, a direct expression is given to you. You can convert this into a K-map, right? You already know how to do this. Simply put a 1 in all those cells whose number is written here, 3, 4, 6, and 7. So cell 3, cell 4, cell 6, and cell 7 will get a 1. All other cells will get a 0. And now how the simplification process works is, it's very simple. So all you have to do is make groups of 1s in adjacent cells, right? Group together all the 1s that are present in adjacent cells. Now, adjacency is important to define. From this chart, you can see that these two cells are adjacent. These are pretty easy to see. But there's another definition of adjacency, which is that this one is adjacent to this one. And that is established once we understand the fact that this actually needs to be visualized in a 3-dimensional manner. So what happens is, this chart must be seen like this. So this is not a 2D map, rather this is a 3D cylinder, right? So this end then continues from this side, right? This end is connected to this end, so that this forms a cylindrical surface, which is why this cell is adjacent to this cell and this cell is adjacent to this cell. And by that definition, you can see that this one is adjacent to this one, right? So all you have to do for the simplification of K-maps is group together 1s present in adjacent cells. And the idea of grouping is that you should form groups which are as large as possible. In this case, only 2 1s can be grouped together. No larger combination is possible. But if, for instance, there was a 1 in cell 2, then this entire set of 1s, 4 1s, would have formed one group. But in this case, these are the only 2 options available. And the other rule is that you should try to avoid overlapping groups, right? So what that means is, if you've already formed this group and you've already formed this group, there's no need to form this group. There's no need to repeat ourselves, right? No need to overlap the groups. And by following those rules, we can see that these are the 2 groups that we finally form. Now these are the final groups. And the next step then is to name these groups. Now we have to represent these two groups in terms of A, B, and C. Now the naming rules are very simple. You have to look at those variables which do not change within this group, right? Now in this group you can see that A is 0 and A is 1. So A changes, right? A does not remain constant. But in this case, both B and C remain constant, right? The value of both B and C remains 1 for this entire group. So the name of this group is BC, right? Similarly, for this other group, we can see that while A remains the same, A is 1 for this one as well, and A is 1 for this one as well. B changes from 0 to 1. For this one, B is 0. For this one, B is 1. C remains 0 in both cases. For this one also, C is equal to 0. For this one also, C is equal to 0. So the name for this group should be A, C dash, right? A, C dash. And this completes the expression, right? So this is how simplification is done. So for the given function, this is the simplified expression that you have now obtained upon simplification of the given K-map. All right. Now, here's another important thing to understand about K-maps is not everyone forms the same kinds of groups. So it's very possible that your K-map might look very different from someone else's K-map, depending purely on how they have decided to group the ones together, right? Because in this case, you might have noticed this group was also possible, even though we said that in this case we are going to avoid this because we have already formed this group and we have already formed this purple group as well. But suppose we hadn't formed this black group, then this would have been one of the groups, and that means someone else could have an additional term here, which is that would have been AB. All right, so not every result of K-map simplification is same for everyone. It depends entirely on what group that person has chosen to make. All right. Now, what's important to understand at this point is this plus sign. Why have we used a plus sign? Why are we using plus? And that is because the given function was this. The given function was written in terms of min terms. There was a summation sign, which is why our expression here has plus. Again, the significance of this, of the summation sign and plus, will become simpler as we proceed. And this is what I was talking about earlier. So additional term, if you go ahead and use this group as well, the green one, then you would have gotten an additional term AB, right? But the rules for K-map simplification, all you have to understand is you have to form the largest group possible and you have to avoid overlapping. But again, this is not wrong, all right? But since the idea, the whole point of this is to perform simplification, so better to go with BC plus AC dash rather than BC plus AC dash plus AB, because this is much simpler than this whole thing. This is not wrong, but this is preferred. All right, let's take another look. Suppose this is the function that is given to us. This is a 4-variable function now, right? Again, there's a summation sign, which means these are min terms, which means all the cells whose number is written here, we have to put a 1 for those cells. So this is the K-map that we get. This is the filled in K-map for this given expression. And now how do we simplify this? Again, we have to start forming groups. And we have to start with the largest group possible, which you'll notice in this case is this group of 4 ones right in the middle. Okay, so this was pretty simple to see. And since we know that this is not a 2-dimensional map, but rather a 3-dimensional surface, that means this, 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 and this is also a group. And to help you understand that, do you get an idea of that visualization? Here's a diagram. So what happens is, suppose this is a 4-variable K-map. First, we combine this edge with this edge to get this kind of cylindrical surface. And then we combine this edge with this edge, right, to get this donut shape. So this is how you try to get a 3D visualization of a 4-variable K-map. So a 3-variable K-map looks like a cylinder. A 4-variable K-map is supposed to look like a donut, which means that this cell is adjacent to this cell and this cell is adjacent to this cell, which is why these corner ones are actually part of the same group. Okay, so these are the groups that are formed now. Again, we have 2 groups. And now the next step is to give names to these groups. So basically represent these groups in terms of A, B, C, D. And the rules for those are simple, right? We have to look for those variables that do not change across the given group. So let's first start with this central group. For this group, A changes from 0 to 1, but B remains the same. And on this side, C changes from 0 to 1, but D remains the same. So this group should be BD. Right, this group should be BD. And for the purple group, we can see A changes from 0 to 1, but B remains the same. So we get B dash. And then C changes from 0 to 1, but D remains the same, 0. That means we get D dash. So this now, when we combine these 2 groups together, we get our expression, our simplified expression as BD, which is this group, plus B dash D dash, which is this group. Again, other solutions are also possible. Now, since we already stated that we should go with the largest group possible, but it could be possible that someone forms a group like this, someone forms a group like this. Many versions are possible, which is why we are saying that other solutions are also possible. None of those solutions are wrong, right? But the point is, the most simple solution is the best. And in this case, this is the simplest solution that we can get. We can get other variations also, but this is the simplest one. Because here the grouping, we have done the largest possible grouping. In this case, 4 ones could have been grouped together, so we have done this. Plus there is no overlapping, right? So we should follow these rules. Start with the largest possible group and avoid overlapping as much as possible. Right? Simple enough. Now here's an exercise. Suppose this is another set of min terms is given to us now, and we are required to simplify this, right? Since these are min terms, that means that all the cells whose number is written here should get a 1 and all the other cells should get a 0, right? So this is what the K-map for this expression will look like. And then for simplification, all we have to do is start making groups of adjacent ones, right? And this is the best. Again, multiple solutions are possible, but this is one of the best possible solutions. So first we started with this bunch of ones, and then we saw that these 4 ones could have been grouped together, and then we're left with this one. So this is the grouping that we go with, and then we're simply left with the task of giving names to these groups. So right, this one becomes BC, the green one becomes B dash D, the purple one becomes BCD dash, and this is the simplified expression. This is how we simplify Boolean expressions. So either a truth table could be given to us or a simple expression like this could be given to us. The idea is we have to first draw a K-map, and then we have to start grouping the adjacent ones together, and then we have to give names to those groups, and that gives us the simplified expression. Again, the expression with the fewest number of terms is the best possible solution, because that is in fact the simplest. All right, now the maps that we have seen so far can be referred to as sum of product form, SOP. Sum of products. Why? See, take an example. This is the exercise that we just solved, and this is the expression that we got after simplification. You see here, these 2 terms, these 2 terms, these 3 terms, we are taking the products of these terms and then we're adding them. So what this essentially is sum of products. That's why it's called SOP. In SOP, we go with min terms, and in SOP, the submission sign is present, right? And in SOP, we add the product terms. We take the sum of the product terms. Another representation of K-maps is also possible. It's called product of sum. So in that case, we take product of sum terms. Rather than taking sum of products, we take products of sum. Here's an illustration of what that look like. So here's a truth table. This is the same truth table that we discussed when we were talking about min terms, right? So this is the same truth table. We have already seen how to represent this truth table as min terms. Here we see how to represent the same truth table as POS. And in this form, we use pi instead of summation, which means product. So summation represents sum, pi represents products, and 0, 2, and 3 represent those cells or those rows which have an output of 0. In case of SOP, we were talking about those cells in the K-map or those rows whose output was 1. But in case of POS, we talk about those cells of the K-map or those rows whose output is 0, right? So this is the 0th row, 0th row, 1st row, 2nd row, 3rd row, 4th, 5th, 6th, 7th. And we're focusing only on those rows whose output is 0. Instead of 1 now, we're talking about 0. So this is what is different between SOP and POS. In case of SOP, we are concerned with the output 1. In case of POS, we are concerned with the output 0. So here's the formal definition of max terms. A max term is a Boolean expression resulting in 0 for the output of a single cell and 1s for all other cells in a K-map or a truth table. So we have already seen this in this specific truth table. We have 3 max terms, right, corresponding to these 3 rows. This one, this one, this one. Now you'll notice something interesting here. These terms are represented in terms of plus. So these are sum terms. Now you'll recall when we were talking about min terms, the first min term was this one, and it was represented as A dash B dash C. A dash into B dash into C. That was the first min term. That was product. Now it's about sum. So the first max term, which is this one, is represented as A dash plus B dash plus C dash. Similarly, this one is represented as A dash plus B plus C dash, right? So this is different here. So this must be kept under consideration. So this is how we define a max term. So now you know min terms and now you know max terms. In case of min terms, we use summation symbol and those correspond to those rows whose output is 1. In case of max terms, we use the pi symbol, which is for product, which stands for product, and in this case we are more concerned with the zeros rather than the ones. So this truth table can be represented like this in terms of max terms, which is what we saw earlier. We use pi symbol and we refer to those rows whose output is 0, and that completes your all you need to know about max terms. Now let's understand something about the K-map. So the same K-map can be represented in terms of SOP as well as POS, right? Because all you have to do is switch between the zeros and the ones. If you are more concerned with the ones, if you're considering the groupings of the ones, if you are simplifying the K-map by considering the ones, what you get is your SOP, right? What we've done so far. So in that case, first of all, you'll represent this K-map in terms of the min terms. You have to write the names of all, the numbers of all the cells which contains 1, right? These are the min terms, and you have to put a summation sign. But the same table, if now you consider the zeros instead of the ones, you get a POS. You get POS, the product of some form, for the same K-map, for the same Boolean expression, right? Now in this case, you'll write down the numbers of those cells which contain zeros, and you'll put a pi symbol. So the same K-map, you can draw the same K-map for a SOP expression or a POS expression. The only difference is, are you more concerned with the ones or are you concerned with the zeros? So let's see how to simplify a K-map in a POS form, a K-map which is given in the form of POS. So suppose this is the expression, this is the Boolean expression that is given to us, and from this pi symbol you can see that this is a POS form. So if in the question a pi symbol is given, what you need to understand is that these are the max terms. That means cells with these numbers are going to contain zeros, and then you're going to group those zeros. So just forget about the ones now, all right? So again, we draw a K-map, a 4-variable K-map. You know already how to draw this. For all the cells whose number is written here, you have to enter a 0, right? And for all the other cells, just put a 1 there. And the simplification process is the same that we did in case of SOP. The only difference is now you're concerned with the zeros. So you're going to form the groups of the zeros, right? So start with the largest possible group that you can find, and the second rule is try to avoid overlapping as much as possible. So the first group that you can form is this one. All right, variations are also possible. You have to remember that. Someone else could have another set of groups, right? So in this case, we're proceeding with this one. Say this is the first group that you form, this is the second group that you form, and this is the third group that you form. So now with these three groups, you have covered all the zeros in this map. Now all that's left to do is represent these three groups in terms of ABCD, right? In terms of these 4 variables. So for the first group, this black one, we can write it as this, right? Now, two things to notice here. First of all, this is a POS. We're talking about POS simplification, which means product of sum, which means this will be a sum term. If we were talking about SOP, this would have been C dash into D dash and then plus something else. For the other group would have been plus something else, and then for the other group it would have been plus something else. But now it is POS, so it will be product of sum. Sum terms will be multiplied. So this is the first sum term for this black group. The second thing you have to notice here is both C and D are the only variables that are not changing, so it makes sense that the name for this group would contain C and D. But you see that we have written C dash and D dash here. Although C and D are 1 and not 0. So dash we write in case when the variable is 0, and without the dash is the variable when it is 1. But in case of POS, this is reversed, right? So everything is reversed when we're talking about POS. In POS, we are grouping zeros instead of 1, and in POS, when the variable's value is 1, it is written as dash. That's why both C and D, although they are 1, they are written as dash, as if they were 0, right? So C dash plus D dash. Now following the same rule, what would be the name of this green group? In this case, you can see that A and B are not changing, and C is also not changing. So this would be A dash plus B dash plus C. Just remember, we are reversing the whole situation here. So although A and B are 1 and C is 0, A and B will be dashed and C will not be dashed, right? Plus, they are added, and this term is then being multiplied with this term. So you can see how this is a POS form. This is a product of sums. And finally, for this blue group, see, for this group, the value of B doesn't change, and here C and D don't change. So this will be B dash plus C dash plus D. All right, and again, other solutions are possible. Here are just two variations of the same equation. For the same equation, for the same K-map, someone else could have a different kind of grouping. You could follow this kind of grouping, in which case your final solution would be different. In this case, your final solution would have been different. The final simplified Boolean expression would have been different, right? So it all depends on how you make the groups. The point is, start with the largest group. You have to include all the zeros in case of POS, right? And you have to avoid overlapping as much as possible. And when you follow those rules and when you give proper names to these groups that you have formed, the answer will not be incorrect. All right. So that's it for this video. Just a quick recap. So far we have looked at an introduction to K-maps. We have talked about 2, 3 and 4 variable K-maps, and we've talked about K-map simplification. And in that specific topic we talked about min terms, max terms, and we learned about sum of product form and product of sum form, and we discussed how to simplify K-maps in both SOP and POS forms. Now in part 2 of this topic, in the next video, we are going to talk about 5 variable K-maps, and then we'll see how to simplify these 5 variable K-maps. Specifically, we'll talk about two main representations of 5 variable K-maps, which are overlay maps and reflection maps. And then we'll talk about K-maps with don't care conditions. So we'll see what these don't care conditions are and how to deal with them when they arise in a given K-map.